So we're going to do fit indices, and really we're going to now take what we learned in the last set of examples over just path models and do some real path models this time that are identified and look at their fit indices. So kind of take path, add fit indices to it, and see what happens. So this example is from the Klein book, and where we have two different competing models of health. And we're going to build those models, compare them based on fit indices, determine if they're nested, and see which one's better. So these are the two models. One of them is a psychosomatic approach to illness symptoms and looking at how lowered socioeconomic status and neurological dysfunction lead to lower morale, which is going to create illness and poor relationships. And so you'll see that there is a covariance here. Remember, lavaan does that for you automatically. It's going to estimate my two variances here. This morale, because it's an endogenous variable, has an error term. And this is labeled D for disturbance. Same thing. And then these two out here, also since they're endogenous, have error terms. Another way to think about this would be more of a conventional medical approach, where illness and neurological dysfunction predict lowered socioeconomic status, morale, and relationships. And so this is different ordering and set of paths for these two models. So in the lecture part of this video, we talked about nesting of models. So can I make this model be this model? Yes, it's a lot of changes, but you could. So I could take illness symptoms here and move it and add a path here to diminished SES. And then I would have to make... Okay, well my thing froze, so I'm going to kind of back up a sentence just to make sure I catch everything. The question is, can these models be nested, right? So, can I make this model into this model? Yeah, it's kind of complicated, but you can. So I could draw a line from illness symptoms to SES like it has in this one. And so in theory, in this model, that line is 0. So we force them to be unrelated. I would have to take low morale and make that path a 0. And so I'm essentially would be changing the paths. So I can make these models out of each other. It just would be kind of complicated. But they are nested. So the correlation matrix is from the Klein book, so I've included that in my R code here. So load lavaan and the simplot, so we can look at the pictures here in a little bit. There it goes. And so let's first load the data. Okay. I've stacked this data so it's nice and readable, so I can tell that I haven't missed a spot anywhere or really replicated numbers. And by making it look like this, I can compare that to the one printed out for me. But at the moment, while it's complete now, the variable labels are not what we need. So remember, the second thing to do is always, and remember the one that indicates that yes, it is a correlation table. Apostrophes are hard today. Next thing you always want to do is name the data. So use column names and row names, and then give each piece a specific name. So I just hacked some names together based on what they had told me the data was. Now if I click on data, I've got my 5 columns and 5 rows, and those look correct. And let's build our models. So let me back up. So model 1 here, like I said, I always like to start on the right and work my way backwards. So illness symptoms is predicted by low morale. So I'm going to have a line that says illness, tilde, low morale, or just morale. Poor relationships also predicted by morale. So relationships, tilde, morale. Morale, though, is predicted by SES and neurological dysfunction. So I've got morale is predicted by, so the tilde, SES plus neuro. And this covariance area, I can define it, but it's automatic for exogenous variables, because if you remember in the last example, we missed our degrees of freedom calculation because we forgot about that one. So that is automatically included. For the second model here, if I start kind of here at the bottom, poor relationships, tilde, low morale, and neuro. Low morale is going to be tilde predicted by SES and illness. SES is predicted by illness and neuro. And that should cover all of our different arrows. Oh, and then I had the picture again. My bad. But let's see if we got that from my notes here. Okay, so I have illness is predicted by morale, relationship is predicted by morale, and morale is predicted by both. So that's model 1. Model 2 is that SES is predicted by illness and neuro. So I've got SES. So I started at the top. These two arrows. Morale should be predicted by illness and SES. Morale, SES plus illness. And the order doesn't matter. And then relationships predicted by neuro and morale. Do make sure you have a enter between each one of these. So they should be on separate lines. That's not me stacking it like this. That has to be like that. Additionally, the order that you put these in doesn't really matter. The left or right part does. So the order on each side of the tilde, not so much. The sides that they're on for the tilde does matter, because that tells you what direction the arrows are going. But again, this is why we always draw the picture, even if it's hideous, and make sure it looks right. Okay, so we have put the data in, labeled the data, and built our model. The next step is to run the model. So we've got some of our model. We've got our sample covariance, because we don't have the entire data set, and then the number of observations. And then let's look at the output. So we did r squared equals true before. You can use t or true, the word true. Now we're going to add fit.measures equals true. And so we're adding on to the summary, really. And then in the next couple of sections, we're going to change the models. So we're going to kind of work our way by adding on pieces to look at from the summary output, but also changing our types of models that we're building so that we're not doing just a whole lot at once. You can also use fit measures of the model to do them separately. So I'll show you both here in a second. So just model 1 here, I'm going to calculate overall, and then I'm going to get a summary. So I've got fit measures equals true out here. So what happens is it sticks all of those at the front. So here is my chi-square. I have 4 degrees of freedom left. Let me see if I can calculate that real quick. So 4 degrees of freedom. I got 1, 2, 3, 4, 5 squares times 6 is 30, divided by 2 is 15. And we are estimating 1, 2, 3, 4 paths, 5, 6, 7 errors. So 8 here for this, 9 and 10. Oh, I missed one. I can't count, right? So I got 1 covariance, 2 variances. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, so something's being estimated that maybe I'm not expecting. That or I can't do math. So let's go down here and figure it out. Okay, so I've got illness to morale, morale to illness, morale to relationship, and then these two predicting. So 1, 2, 3, 4. I've got 1 covariance, 3 variances. Okay, that's what I'm missing. Okay, so this one also gets a variance because it is exogenous as well as endogenous. So it's going to have a variance out here too. That's the one I missed. Alright, when we look at the picture here in a second, we'll see that a little better. Or actually, let's just do it now. So the thing I missed was the fact that both of these got variances, right? So this one also as well. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Alright. That's why I like making these pictures. They're a little easier to see. Plus they have all the numbers on them. Anyway, if I look at this output, it sticks all the fit indices at the beginning. So here is the chi-square statistic. Well, damn, that's significant. So that doesn't do me any good. But again, we talked about how it's problematic because it's always significant. So what I'm going to do is stick that information here. So I think it was 40.303. And it's 4 degrees of freedom. So I'm just going to stick that there. The minimum function test statistic. So this is the baseline model. So it also shows us now that we've asked for fit indices that statistic where none of the paths are significant. So I got my degrees of freedom back because it says all of these paths don't count. So it considered the four paths here, and then 5 paths here, and that's where the degrees of freedom came back. Okay. So it gave us back 1, 2, 3, 4, and I think it's estimating something else. We'll zoom out here. All right, so I got 1, 2, 3, 4, and it added a covariance between these two, right? So that is the piece that we missed a minute ago calculating our degrees of freedom, is this relationship here between these two variables, which I probably didn't really want, so I should probably go back and exclude that at some point, because they're kind of hanging out there on the end. So that, I think, is something that lavaan did automatically for me that I wasn't expecting. All right. If you do want to turn that off, I can kind of show you how. This is not something I really planned for you to have quite yet, but that is illness and RIT, or LT, relationship. What I could do is do relationship, ship singular, tilde tilde, so the correlation between the two, illness, and do 0 times that. So I can make that path 0. I hope, anyway. Okay. And now I should have gotten a degree of freedom back. You see, I have 5. And if I make that picture, it will make that path go away, which is probably more of what I wanted, since I didn't expect a correlation between these two. Right? Now, neurological and SES I did expect, but these two on the end I didn't. Okay? And so there are some times that lavaan will do some things that are sort of given a normal CFA parameter it would expect you to do, but you didn't necessarily want. It will not do that on these models because they are predicting each other. Okay? It's because they're hanging out here by themselves without sort of any relationship between them, I think, is the issue. All right, where was that? We built the model. Now we're looking at the output. I'm going to go back to my original without that corrected issue, though, because that is what the rest of this is based on. So let's look at that summary. Okay. So let's say we wanted to include that. Okay. So here's my model baseline statistic. And that would be if all the paths were 0. Our model has a lower chi-square, so that's good for us. So no relationships is much worse than having those relationships. Woohoo, party! Here's CFI and TLI right here at the top. You can tell they're pretty popular because they came up in the output. So I got 0.91 and 0.79. So pretty different predictions there. Go to 3 decimals if we're going to compare by CFI. So 3.786. All right. What else we got? We got some, here's AIC and BIC. So I'm going to tell you to include AIC so we can do non-nested model comparison. Although I don't know how to interpret 6,000. Right. This one I can tell is good. This one I can tell is maybe not so good. And I don't know how to interpret that. Here's SRMR, 0.065. Now, reporting these, most of the time you do not use a trailing 0 because they do not go over 1. And then here are actual parameter estimates. I missed RIMC. There it is. I skipped it, sorry. So RIMC is 0.14. It's not very good. And then the 90% confidence interval, which you can write as 90% CI, square brackets, it's a little unusual, is 0.102 to 180. And normally you don't include that space. I just try to space it out so you can see it a little better. Now there's 2 that I've told you to include that aren't on here, so how do I get those? Well, lavaan doesn't show you everything it has because otherwise you would be looking at tons of stuff. So what you can do is type just fit measures. You You can do it with a capital M or not. Model1.fit. And then you can see all of the possible ones that are calculated for you. Oh boy, it's a lot. So here's NNFI, which is the same thing as TLI, so you'll notice they have the same number. Here's the regular NFI that I'm telling you to look for. So 0.897. Okay, that agrees more with CFI than Tucker-Lewis. But there's actually a couple of different types of BIC. There's RMR. Now, when you're looking for RMR, that's not the same thing as SRMR. In this particular example, they happen to be exactly the same, but it's not always going to happen. There's like 10 different RMRs. And then the ECVI is here last. So 0.12. Okay. It does not have the same rules. It does go over 1. It does not have the same rules as these. Right? It is in the same family as AIC. So smaller is better, but it can be 2, 3, 4. So it just happens to be tiny. So overall, what would I say about this model? It's okay. Right? RIMC is no good. SRMR is good. CFI is acceptable. TLI is not. NFI is probably acceptable. And then these two I'm going to use for model comparisons. So I really have a mixed bag. If I go back and look at the parameter estimates, so I'm going to run my summary one more time. They're all significant. Neuro predicting morale is technically non-significant. It's close. The covariance between illness and relationship that I didn't really want anyway is non-significant, so that's good to know. I could probably exclude that and gain a degree of freedom back. Right. But if I look at my R-squareds, I am predicting illness and relationship pretty well, but maybe not morale so much. So I don't know if this is necessarily the best type of model, given that some of these things aren't working. So let's try our alternative model. Go back here, see what I'm forgetting. So we're running each model, and we're going to compare these models, and then let's run model B here. Alright, so here's model B. You will notice that it doesn't necessarily have any extra covariance arrows we weren't expecting, right? So if I go back and I look at this, I would say, what are we estimating? So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think we said there was 15 possible options. Right. So we have 3 degrees of freedom left. Whew. This time we got it right. Okay. So that's my sort of push. Always look at the picture, because sometimes you won't get it right and you won't know why. And in the last example, it was because it added an extra covariance we weren't expecting. Alright, so I'm looking at my summary here. Let's see. I personally like to leave fit statistics off and do them separately because I find there's just too much output here. But you can go either way. Alright, look at this non-significant chi-square. Oh, that's so cute. That's because this is fake data. And so this model is clearly going to be much better. It is a slightly different model pathwise. So the degrees of freedom are still going to be the same because it's saying no paths are significant, but the fit statistic will change for the baseline model between the two. That doesn't matter so much for our purposes, but that's why it's different. So I'm going to fill in 3 and 3.245. Let's look at some of the rest of these. So CFI is 0.999, Tucker-Lewis is 0.998. So they're both excellent. Can't get much better. AIC here. Copy that bad boy. So technically this one is smaller. Not technically, it is smaller. Let's see. RIMC is 0.013 and 0 to 0.08. And so we got our 90% confidence interval is 0.000 2.018. And that is a good range. It's very small, so both ends of them are within the excellent range. If you wanted to look at P close, that's this thing right here, and it's 0.742, which is greater than 0.5. It's 5.0. I don't know if that's a super popular idea to do, but there it is. SRMR is 0.16, sorry. And then I need to use my fit measures code here. To get the other two. So NFI here, 0.992, and ECVI, 0.045. What can I say about this model? Well, it's great because that is the model the data were made from, and so it looks really good. This RIMC, this is not significant, which is magic. This RIMC is good. This SMRMR is good. All three of our fit indices, comparative fit indices, are great. This model has the lower AIC and the lower ECVI. So if I used non-nested criteria, this model B is significantly better than Model A. But I also could use my chi-square because it's nested. So we're going to do two different ways to do this. ANOVA is arguably much easier, but I think it helps if you understand what the ANOVA is doing. So I'm going to type that at the bottom here. So the first thing I did is I turned off scientific notation. So this code option SciPen equals 999 will turn off scientific notation just so that you can see these p-values a little better. I took p chi-square, so this is going to calculate the p-value given these chi-square statistics. I subtracted Model 1 minus Model 2 here, so that's the chi-square difference, so 37 points. 4 minus 3, that's the degrees of freedom difference, and I did that in the way that it was positive, otherwise it'll get very grumpy with you. Lower tail gives false so that I get the tail end of the distribution, which is what you want. So that p-value is less than 0.001. So a chi-square difference test says that they're significantly different. Now what the ANOVA function will do is it shows you actually AIC, so those numbers will repeat, and then it takes our two chi-squares here, creates a chi-square difference between the two, degrees of freedom difference, and p. So these three numbers out here are what we did here manually. You can do either one. ANOVA, like I said, should be easier, but just so that you know what this is doing, that's where the numbers are coming from. Okay. Say, yes, B is significantly better in any one of the ways that we can test that, and also has a significantly better CFI. So we can test here a chi-square difference, that's significant. We can test here at a CFI difference, it's greater than 0.01, which is the criteria for that one. Okay, those are for nested models. We can look at both of these two for non-nested models, or nested models, it doesn't matter, and both of them are lower for Model B. So thankfully we're all in agreement here. Model B appears to be better. And then if you just look at the fit statistics, they're clearly much better. If I look at the parameter estimates, scroll up here, those seem to be more appropriate as well. So they are all significant, and we're estimating more of the variance better. One interesting thing is clearly fake data. Look at those z-scores, they're all the same. One thing to notice that I think I haven't mentioned before is the standard errors are very low in both models. And that is normal to have standard errors that small because you have very large sample sizes. But one thing to notice, like if you're looking at a model that maybe seems like it's not working too well, there might be one standard error that's really large. That's usually a sign that something's gone wrong. So something else to look at is standard errors. Alright, so even though both models have nice predictors, these predictors are significant, the fit statistics is really what distinguishes the two. But then I also would go back to theory. does it make more sense that this conventional medical model is better than a psychosomatic or psycho whatever it was model? And so theory really drove both of those, but which one has more support in the literature? So adding the idea of paths, even though these are all still pretty close, I mean, this is close. Even though the paths are significant, adding fit indices and theory to create a whole picture of the model rather than just focusing on fit. Even though in this particular lecture we're talking about fit because that's what I'm trying to get you to learn, but reminding you that the purpose of SIM is to talk about the big picture. Does the model work? Are the paths significant? Is the fit okay? Does it theoretically make sense? So getting all of those as a package deal rather than just focusing on one particular fit index.